There is this almost universal experience for anyone who has ever built a piece of software. Doesn't matter if you are a seasoned engineer or just like tinkering on a weekend project.
Oh, absolutely.
Right? You are sitting at your laptop, you write a database query, you hit run, and it absolutely flies. It feels instantaneous.
It really does.
But then you take that exact same code, you deploy it into a production environment with real user traffic, and suddenly the whole thing just crawls.
Yeah, it is the classic works on my machine paradox. But the thing is, it's operating at this massive structural scale that catches almost everyone completely off guard.
And usually, our first instinct is to try and solve it by just throwing money at the problem. We spin up more CPU cores, we, buy more RAM.
Exactly, just brute force it.
Right. But our source material for today's deep dive, it's this fascinating engineering guide called Editing Spinners versus Silicon: How Database Engines Cheat Physics to Persist Data. It argues that we're looking in the completely wrong place.
We really are.
The real bottleneck isn't a lack of compute power at all. It's actually the physical friction between your high-level database algorithms and the unforgiving laws of physics governing your storage hardware.
Because, we tend to think of data purely as abstract information, right? Like a string of text, a user profile, a financial transaction.
Yeah, just lines of code.
Exactly. But to actually persist it, to guarantee that data survives if, say, someone yanks the power cord out of the wall, that abstract information ultimately has to become a physical state change in the real world.
Bridging that massive divide from a simple, declarative SQL query all the way down to the physical hardware is our main mission today.
Okay, let's unpack this. Think of the journey of a single piece of data, like a multi-stage relay race.
I like that analogy. It starts as pure software logic in the operating system, it travels down through the block layer, and it ends as literal physical movements or trapped electrons on a physical disk. To understand why your database slows down, we actually have to start at the finish line of that race. We have to start at the literal bottom of the stack.
Because physics dictates the ultimate performance ceiling. No matter how clever or optimized your software algorithms are, they just cannot outrun the physical limitations of the medium they are writing to.
So let's look at the old school medium first. Hard disk drives, affectionately known in the industry as spinners.
Right, the classic hard drive.
Yeah. If you crack one of these open, it's basically a microscopic, high-tech record player. You have these magnetic platters spinning at incredibly high speeds and a mechanical actuator arm that literally has to physically swing a magnetic head over the correct track.
And then it just has to wait.
Right. It literally just waits for the exact right sector to spin underneath it.
And that requirement for physical movement creates a massive mechanical bottleneck. If we look at the raw math, just the seek time, the time it takes to swing that actuator arm to a random track, that takes between 2 to 8 milliseconds.
Milliseconds. In computing time, that's an eternity.
It's an absolute lifetime. And then you have the rotational latency on top of that. The formula for maximum rotational latency is 60,000 divided by the drive's RPM.
Okay, so if you're a database administrator, right, and you're just desperate for speed, and you upgrade your server from a standard 7,200 RPM drive to a screaming fast 15,000 RPM enterprise drive, you might logically think you've doubled your performance.
You would think so, yeah. But mathematically, you are only saving about 2.17 milliseconds of average rotational delay.
Wow. That is almost nothing for the cost.
Exactly. It's a hard physical limit bounded by, material physics and the aerodynamics of spinning platters that fast without them just shattering. If your database is doing random reads or random writes, these physical mechanical movements completely devastate performance. You are ultimately capped at a miserable 100 to 200 input-output operations per second, or IOPS.
Which brings up the savior of modern architecture. Solid-state drives, or SSDs.
Yes, finally.
Zero moving parts. We trade those fragile mechanical platters for quantum silicon.
We shift from electromagnetism to trapping electrons inside these complex, microscopic hierarchical arrays of silicon cells. And what's fascinating here is how the underlying logic gates actually dictate the physical layout of the drive. Most modern SSDs use NAND flash, which gets its name from the naughty digital logic gate.
I was reading about this in the guide. The memory cells in NAND flash are daisy-chained sequentially in series, right?
Yeah. Sharing those source and drain lines across multiple cells drastically reduces the number of physical contact wires needed on the silicon die.
Which makes them cheaper to produce.
much cheaper. That single architectural decision is exactly what enables the extreme terabyte-level storage density and the incredibly low cost of modern SSDs that we take for granted today. But, and this is big but, because they are wired in series, you physically cannot access individual bytes of data. You are forced to read and write in large page-aligned chunks.
Wait, hold on. So if SSDs have absolutely no moving parts and they operate at the literal speed of trapped electrons, why do we have any bottleneck at all? Didn't we just completely defeat physics?
Well, we defeated mechanical physics, certainly, but we introduced a profound new challenge of solid-state physics. The fundamental catch of NAND flash is this. You cannot overwrite data in place on an SSD.
Meaning, if I have a specific row in my database, say I want to update a single user's email address, the SSD can't just go in and flip the electrons exactly where that old email address currently lives.
Exactly. To update that single piece of data, the SSD must write the new version of the email address to a completely fresh, pre-erased page somewhere else on the silicon. It then has to deliberately mark the old physical page as stale or invalid.
But if you're listening to this and you're thinking about how your laptop works, your operating system doesn't know that's happening, right? The OS still thinks it's writing to the exact same logical block address it always has. So how does the computer even know where these new physical pages are?
The SSD has to fake it. It has to constantly translate the operating system's logical addresses into the ever-shifting physical reality of the silicon. And doing that requires a dedicated translator known as the Flash Translation Layer, or FTL.
This blew my mind in the source material. This FTL, it isn't just like a software driver running on your main CPU.
Not at all. The FTL is a self-contained embedded system living right there on the physical SSD circuit board.
Like a miniature computer.
It is essentially a miniature computer inside your computer. It has its own firmware, its own ARM microprocessors, and its own RAM to hold this massive, constantly updating logical to physical mapping table.
That is wild.
On high-end enterprise drives, there are dedicated DRAM chips physically soldered right on the board for this. On budget consumer drives, they use something called HMB, or Host Memory Buffer, where the drive literally steals a portion of your computer's main RAM to store its map.
It's essentially duct taping a tiny computer to your storage drive just to hide the fact that we can't overwrite data.
That is a perfect way to put it.
And understanding that leads us to the next stage of the relay race. How your operating system and this tiny embedded SSD computer actually communicate. They use a grid.
Right, the page grid.
Yeah. From the running program's perspective, memory is just a contiguous line of virtual pages. The physical RAM chips are divided into matching slots called page frames, and the durable storage disk is divided into matching disk blocks. Traditionally, they all used a standardized size of 4 kilobytes.
And that 1.10 copy pipeline is brilliant for hardware-level coordination. The OS can trigger a direct memory access transfer, pulling a 4 KB disk block straight into a 4 KB RAM frame and map it to a 4 KB virtual page. Zero CPU processing is required to move that data.
But history has a funny way of biting us. That 4 KB standard, it was chosen back in the late 1980s. It was standardized for the Intel 80386 processor.
A very long time ago in tech years.
Exactly. Back when a top-tier computer had maybe a few megabytes of RAM. 4 KB blocks made perfect sense.
But today, we have massive database servers casually running 128 gigabytes of RAM. Think about the logistics of building a massive modern skyscraper. But you are forcing the construction company to ship it one single individual brick at a time.
The logistical overhead just completely collapses the system. The CPU has a specialized hardware cache called a translation look-aside buffer, or TLB. Its only job is to track where these virtual memory addresses physically live in RAM.
Okay.
With a 128 gigabyte server, you are asking the CPU to track 32 million individual 4 KB pages. It completely overwhelms that tiny TLB cache.
So what actually happens inside the processor when that cache gets overwhelmed? Like, why does it slow down my database query? It causes a phenomenon called TLB thrashing. Because the CPU can't find the memory address in its fast cache, it has to pause whatever database calculations it was doing and essentially play a painfully slow game of Go Fish in the main system RAM.
Oh, wow.
Yeah, it has to physically walk through the page tables just to find where the data lives. Under heavy workloads, a top-tier CPU can spend up to 30% of its total processing time doing absolutely nothing but translating memory addresses.
30%. That is a massive silent bottleneck.
It's huge.
And it's exactly why modern systems are finally starting to shift. The guide mentions databases are moving to 2 megabyte or even 1 gigabyte huge pages. ARM and Apple Silicon chips now natively support 16 KOB pages at the hardware level, and the Linux kernel is adopting large folios to dynamically group memory together. You absolutely have to match the block size to the modern scale of the hardware.
This raises an important question, though. What happens if you don't? What happens when the operating system stubbornly sends those tiny 4KB blocks, but the physical NAND flash pages on a modern high-density SSD are actually 16 KB in size?
Right, because the SSD can't just write 4KB if its physical grid is drawn in 16 KB chunks.
Exactly. That collision at the hardware boundary triggers the absolute nightmare scenario for an SSD, the read-modify-write cycle.
Oh no, that sounds bad.
It's terrible. If the OS sends a 4KB write, the SSD controller has to physically read the entire surrounding 16 KB page from the silicon into its internal DRAM. It merges the new 4KB change into that buffer and then writes a completely new, fully merged 16 KB page back to a fresh spot on the flash array.
Let me get this straight. If my database updates a tiny 128-byte record, say a user status flag, the SSD might be secretly reading, merging, and writing 16 kilobytes of data behind my back.
It does, every single time. And out-of-place writes leave behind all those stale, invalid pages we discussed earlier. The SSD's FTL has to constantly run background garbage collection.
Right, to clean up the mess.
Yeah, it has to find physical blocks that contain a mix of stale and surviving valid data, move the valid data to entirely new blocks, and then physically erase the old blocks so they can be used again. Because of this, the drive is physically writing significantly more data to the silicon than your database actually requested.
So the hardware is basically doing exhausting busy work just to keep up.
That busy work is called the write amplification factor, or WAF. In bad scenarios, this hardware WAF can spike up to 10x, meaning for every 1 megabyte your database tries to save, the drive is secretly burning through 10 megabytes of physical silicon writes.
WAV is the silent killer of SSDs. It destroys your input-output throughput, and it literally burns out the physical silicon cells 10 times faster.
But if you were listening to this and you're about to provision a new database server, there is a very practical, actionable takeaway here.
Yes, there is a fix.
You can fix this by formatting your file system and configuring your database to explicitly match the hardware's physical reality. Right, so if you know your underlying enterprise NVMe drive uses 16 KOB physical pages, you force Linux to use a 16 KB block size when creating the ext4 file system. And you configure your database engine like setting MySQL's initb page size parameter to exactly 16,394 bytes.
You align the software and hardware perfectly. Every logical write from the database maps perfectly, one-to-one, to a physical NAND page. No read-modify-write cycle. You bring your hardware WAF back down to a pristine 1x.
It is a beautiful example of software sympathy for the hardware.
It really is. But getting the correctly sized blocks to the drive is still a massive problem if the pipeline itself is too narrow.
Oh, definitely. Taking a hyperfast silicon flash drive and plugging it into a legacy AHCI storage interface is a severe mismatch. AHCI was designed for those slow, single-headed mechanical drives. It relies on a single command queue with a maximum depth of just 32 commands.
I love the analogy the guide used for this. Imagine a massive, high-end restaurant with 32 waiters representing a 32-core database server trying to serve thousands of customers. But all 32 waiters have to stand in a single file line and shout their orders to one single chef in the kitchen.
It's chaos. You get intense CPU spin locks and thread contention. The waiters spend all their time fighting for access to the kitchen instead of serving food. To unlock the massive parallelism of silicon, the industry had to create NVMe non-volatile memory express.
And that operates over PCIe, right?
Yes, it operates directly over the PCI bus, and its scale is staggering. Instead of one queue of 32 commands, NVMe supports up to 65,535 parallel queues, each capable of holding 65,000 commands.
Here's where it gets really interesting. With NVMe, they didn't just add more queues, they fundamentally changed where the queues actually live.
Right. In legacy systems, the command queue lived on the storage hardware itself. The CPU had to write across the slow motherboard bus to the drive. With NVMe, the OS allocates the submission and completion queues directly inside the host computer's high-speed main RAM.
So the OS can give every single CPU core its own dedicated queue.
Yeah.
Going back to the restaurant, every single waiter gets their own private kitchen to send orders to. No waiting in line.
Exactly. The CPU drops a command into its RAM queue in nanoseconds. Then it rings a doorbell register on the SSD. It's a single cycle notification basically saying, hey, you have work waiting in my memory.
Just a bing?
Yep. The SSD controller then takes over, acts as a bus master, and uses direct memory access to fetch the command straight out of the host's RAM, completely bypassing the CPU.
The CPU just drops the package, rings the doorbell, and walks away. So what does this all mean for a massive enterprise database?
It means we've successfully removed the hardware communication bottleneck. But there's always but the Linux operating system still has one more trick up its sleeve that elite databases absolutely hate: the page cache. By default, Linux routes all file operations through its own RAM cache.
Wait, why would we want to bypass Linux? Isn't Linux memory management incredibly optimized? Like, write buffering sounds great on paper. The application thinks it wrote to disk instantly, but it just wrote to OS RAM, and a background thread handles the slow flush later.
It is great for, say, a standard web server or a laptop, but for a highly tuned database, it is a massive penalty. Databases are already managing their own highly optimized user space memory, called a buffer pool. They know exactly which indexes are hot and which data is cold.
Ah, so they already do this.
Exactly. If you let the operating system cache everything too, you suffer the double buffering penalty.
I see. You are storing identical copies of the exact same data in both the OS page cache and the database buffer pool. You could be wasting up to 50% of your expensive server RAM on just duplicate data.
Plus, if you run a massive sequential backup at midnight, it floods the OS page cache. The OS panics, thinking it's out of memory, and evicts all of your hot, crucial database indexes from RAM just to make room for the backup. It's called page cache thrashing.
That sounds like a disaster for performance.
It is, and this is precisely why high-end databases use a special flag called ODirect.
ODirect tells Linux to just back off.
Right.
It establishes a direct DMA pipeline from the database's user space memory straight to the storage controller. The database takes absolute sole control over what stays in memory and what gets evicted.
So let's recap. We've aligned our block sizes to 16 kBp, we've upgraded to parallel NVMe queues, and we've bypassed the OS page cache. The pathways to the hardware are finally pristine.
Right.
But how should the database itself organize the data to keep the SSD happy?
This is the crux of it, the mathematical layout on the disk. Traditional relational databases like Postgres and MySQL have historically used B trees, specifically B-plus trees. They are perfectly balanced wide fan-out trees, but the critical detail is how they handle updates.
B-plus trees rely fundamentally on in-place updates. If you change a user's name, the database rewrites that entire 16 KB tree node back to its exact logical location on disk.
Which was fine for mechanical drives.
Right. On an HDD, this just caused chaotic mechanical arm seeks. But on an SSD, it causes a completely different nightmare because of that out-of-place write constraint we discussed earlier.
Right, the database is demanding an in-place update, but the SSD hardware is physically incapable of doing it. So the SSD is scrambling behind the scenes, writing to new pages, invalidating old ones, and triggering a relentless garbage collection. This is exactly where that 10x write amplification factor comes from.
Exactly. You are rapidly wearing out the physical silicon just to maintain a traditional B tree.
So, if in-place updates are destroying our SSDs, how do modern NoSQL and distributed databases like RocksDB or Cassandra solve this?
They completely abandon the concept of updating in place. They use a structure called a log-structured merge tree, or an LSM tree. In an LSM tree, every single operation writes, updates, even deletes, is treated as an append-only operation.
Let's walk through what that actually looks like.
Yeah.
You want to update a user's profile, you don't go find the old profile and overwrite it.
No, not at all. When the write comes in, it is appended sequentially to a persistent write-ahead log on disk for safety. Simultaneously, it's inserted into a sorted in-memory structure called a mem table.
Which is operating at blisteringly fast RAM speed.
Yes. And when that mem table fills up, say it hits 64 megabytes, it just freezes. A background thread then takes that entire 64 megabyte chunk and fleshes it sequentially to the disk as one massive continuous file called a sorted string table, or SS table.
And because it's a massive sequential write, it perfectly aligns with the physical boundaries of the flash blocks. The SSD doesn't have to do any of that read, modify, write busy work. The hardware wave stays near a perfect 1x. The drive is completely happy.
It is. But if we connect this to the bigger picture, in computer science, there is always a trade-off. We've optimized writes beautifully, but what happens when you actually need to read that user's profile?
Oh, right. Because you never overwrote the old data, there might be, 5 different versions of that user's profile scattered across 5 different SS-stable files that were flushed at different times?
Exactly. To find the most recent, accurate record, the database has to scan multiple overlapping files. This is known as read amplification. And to prevent reads from becoming impossibly slow, the database has to constantly run background compaction threads.
I was wondering how they cleaned up the mess.
Yeah, these compaction threads wake up, read all those overlapping stable files into memory, merge them, sort them, discard all the old deleted versions, and then write out a brand new consolidated file back to the disk.
That sounds like a massive amount of work. We basically traded hardware write amplification for software write amplification. The data you wrote once is being read and rewritten dozens of times by the database's own internal maintenance.
It is. The software wave can hit 30x or more. If your underlying NVMe drive cannot handle that massive internal bandwidth, the database actually has to trigger a write stall. It literally blocks incoming user traffic just so its compaction threads can catch their breath.
Wow.
It's a delicate balancing act. You are intentionally shifting the friction away from the physical silicon layer and pushing it up into the software algorithmic layer.
But whether you decide to use a traditional B tree or a modern LSM tree, we have to talk about the absolute most critical moment in this entire process, the moment of truth. What happens to all of this beautifully orchestrated, heavily cached data if a technician accidentally trips over the server's power cord?
This is the D in ACID compliance, durability. If a database tells a user your transaction is successfully committed, it must survive a catastrophic power loss. But remember, most storage controllers hold incoming writes and a volatile DRAM cache on the physical drive itself to speed things up.
Right, and if power dies, that cache is instantly wiped.
Gone completely.
To prevent data loss, databases use explicit system calls like flesync or flacenasync. They basically grab the operating system of the storage hardware by the collar and say, do not return a success message to me until you have forcefully flushed your volatile RAM caches into persistent physical media.
And executing that hardware flush exposes the massive latency gaps between storage classes. If you call think on a mechanical HDD, it has to physically wait for the platter to spin under the head. That's a 5 to 15 millisecond delay where the database is just waiting.
And on a standard, high-end consumer SSD, like something you'd put in a gaming PC.
It's better, but it lacks hardware failsafes. When it gets in its sync, the controller has to hold its breath and wait for the actual NAND silicon programming cycle to finish physically trapping the electrons. That takes about 1.5 milliseconds. For a synchronous, high-throughput enterprise database, waiting a millisecond and a half for every single commit is agonizing.
Which brings us to the enterprise data center secret. Data center SSDs have something called PLP power loss protection. They actually have physical capacitor banks soldered directly onto the circuit board.
This completely changes the game for database durability. When an enterprise PLP drive receives an infisting command, it writes the data to its fast internal DRAM cache and instantly, like in less than 100 microseconds, returns a success acknowledgement to the database. It completely bypasses the 1.5 millisecond wait for the silicon to program.
Wait, it just lies to the database.
Yeah.
It says it's persistent, but it's still in volatile DRAM. What if the power cord is tripped exactly at that millisecond?
That is exactly what the capacitors are for. If the wall power dies, the electrical energy physically stored in those PLP capacitors provides just enough residual juice to keep the SSD controller and the NAND flash powered on.
Oh, that's brilliant.
It buys the drive just enough time to safely flush the DRAM cache into the persistent silicon cells as it literally dies.
That is incredible. The database gets nanosecond-level speeds, but with physics-level guarantees. So the next time you sit down at your laptop and you write a simple SQL U-bait query, just picture the multi-stage relay race happening under the hood. It's not just code executing.
Not at all.
It is 16 KB logical alignments. It is CPU memory translations for like GoFish and RAM. It is DMA doorbell rings over a PCIe bus, background merge sort compactions, and literal capacitor banks holding a charge. And it's all perfectly orchestrated in microseconds just to make sure a single line of text survives reality.
It is a breathtaking stack of engineering workarounds. And it leaves us with a really interesting thought to ponder.
What's that?
Throughout this entire deep dive, all of these complex mechanisms, the flash translation layers, the OS page caches, mem tables, the write-ahead logs, they all exist for one single reason. There is a fundamental physical boundary between fast, volatile memory and slow, persistent storage.
We spend so much of our compute power just trying to bridge that gap.
We do. So what happens to the entire architecture of computer science? What happens to all these algorithms we just discussed if in the near future the industry engineers a new storage medium that completely erases that boundary? What happens when RAM itself becomes permanently durable?
Now, that is a paradigm shift. We will have to leave that for you to mull over.